Hello everyone, I am Deepak Paliwal. So today in this lecture we will learn about dislocation interaction. As in the previous lectures we have understand that the dislocations, let me happen, the dislocations has stress field around it. Okay, so any particular like age dislocation which we have understand that it has sigma xx, sigma xy, 0 0, sigma zz, sigma yx, sigma yy, and 0 0. So this is for the age dislocation. For the screw dislocation we have various 0 0 0, sigma xz, sigma yz, sigma zx, sigma zy, 0. So both the screw dislocation as well as the edge dislocation has a stress field. So obviously in a material we do not have only a single dislocation, we have a large number of dislocations. So when the question is, when one dislocation, suppose like edge dislocation, is coming in the closer vicinity of the another edge dislocation, as in the previous lecture we have learned that this stress field are short range stress field. So suppose if the this particular edge dislocation which has a particular amount of stress field around it comes into the close vicinity of this particular let me call it 2, this is 1. So if the one edge dislocation coming in the close proximity of the dislocation 2, then obviously both have a stress field, so that stress field will interact with each other. And when the stress field interact with each other, so how we can calculate the force which one dislocation is imposing over other. And the dislocation interaction has a very important significance, because the dislocation interaction only gives the strength in the material. So to analyze this dislocation interaction, a very famous equation known as, let me write with a different color, is pitch Kohler equation. Okay, so the what pitch Kohler equation says, like let me recall that option, like we want to calculate the force. Okay, so we are dealing with the stress field, so I can write stress into a stress cross area, that is my force. So the what pitch Kohler says, like I want to calculate the force vector. Okay, so we have stress is a tensor quantity. Okay, now I have to multiply the area of a slip plane, so which is given a Berger vector. Okay, cross line vector. Now I can also write this equation like this is the tensor dot Berger vector cross line vector. So this equation uh, which is stress tensor and Berger vector is called as G matrix. Okay, multiplied by line vector. Okay, so this is our equation, or rather we can say this is our equation which is important to understand, which is important to understand the various force component involved in the interaction of dislocations. So the important equation I am again writing, force is equal to stress tensor dot Berger vector cross line vector. So here we are dealing with what, we are dealing with the FCC material. So our Berger vector will be 110 kind of. Line vector we can assume like 001 type. So this is for Berger vector, this is for line vector. So let me first write very general equation. Then we will come to the FCC case for particular age dislocation. Okay, so let me write first all the components, like force is equal to, let me write sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, sigma zx, sigma zy, sigma zz. Again bx, by, bz. This is the component of Berger vector along x, y, and z cross ux, uy, uz. Okay, so let me do the dot product among these components. So first fx is equal to uh, sigma xx b1, sigma xy b2, sigma xz b3, I cap. I am just doing simple dot product. Sigma yx bx, I am calling xy chat. Okay, now it is fine. Sigma yy by, sigma yz bz j cap. Let me write here only. Sigma zx px, sigma zy by, sigma zz pz kk. Bracket close, and we have ux, uy, uz. Okay, now this is the very general equation. Now I am writing it for FCC case. FCC case, we know Berger vector is 110 type. Okay, so we have bx component, by component, and bz component 0, and I am assuming for the line vector is 0 0 1. So we will have like 0 0 uz. Okay, so let me write this equation for the FCC case. Okay, highlight this one, I am highlighting this one. Okay, so we have bx component, by component, this component would be 0, like I am highlighting this component 0. Okay, again this component 0, this component would be 0, and let me write again, rewrite the equation. Sigma xx bx, sigma xy by, I cap, sigma yx bx, sigma yy by. Okay, j cap, again I can write sigma zx px plus sigma zy by k cap, and at the last we can write 0 0 uz. Okay, now I can again multiply this. Let me zoom out little bit so that we can see whole equation in one go. Now I am multiplying this. Let me write this particular thing in that fashion. I can write like uh, uz k cap, because we have only this one. So let me write more correctly, uz. Okay, so now just do cross product. Before doing cross product, just revise our understanding regarding the cross product. Just let me write here, like let me switch off. I cross j is k cap, j cross k, I cap, I cross j, again we reach to j, k cross I cap is equal to j cap, and anything in reverse, j cross I, that would be minus k cap, k cross j would be minus I cap, I cap cross k cap would be minus j cap. Okay, so remember this term. Now I am multiplying, or I am doing cross product. Fx like use it multiplied by this one. Okay, so the k I cross kk, that will be your minus jk. So minus, uh, sorry for the disturbance. Okay, let us continue again here, from here, like what we were doing here, like we were multiplying with this particular UZ value. Okay, so let us multiply, like uh, this I cross k will be minus jk, so we have minus here, and again multiply sigma xx px, sigma xy by uz cross uz, and this is 1, so we can write it 1 only. Okay. I'm not writing uz because uz we have already assumed this is 1 only. So again, this is what jk. Here sigma yx bx, sigma yy by, and j cross k is again I cap. Okay, and in the last, if I multiply k cross k, that would be 0. I have forget to mention here, I cross I will be 0, j cross j again 0, k cross k is also 0. Okay, so now we finally left with this particular equation. We have a y component, we have x component of the force. Let me write this equation in the matrix form, like this is not a, this is the complete force part. So this is force, I am writing in this matrix form, yx, let me write more correctly, yx plus sigma yy, uh, again here minus sigma xx minus sigma xy 0, this is bx, bx by 0. Okay, so this is the equation, so I can happily now say this is fx part, this is fy part, this is fz part. If you look at the fx part, now I am assuming like v2 is vy is also 0, so we will left with a very very uh, small equation, sigma yx minus sigma xx 0, bx by 0. Okay, so finally I can write force along x component is sigma yx bx, force along y condition, y direction, minus sigma xx by. I can call it, this is the shear component, and shear component are important in case of the glide motion of a dislocation. So this is where I can call it, this is also I can call it glide force, which is important for the dislocation glide on a slip plane. This is what, this is the dilatation component. So this is a climb force, this is important for climb motion, which we have already understand in the previous lecture, for the movement of dislocation above or below from its original position. So this is for the climb, whenever like any kind of what you can say, the barrier in front of the edge dislocation, suppose this is the barrier, so edge dislocation can move up, it can go beyond, it can pass the barrier, and then again it can come its original place. So here climb up, here climb down. Okay, so the process of like climb up, climb down requires large amount of forces. Let me write some force equation. Again, we have already calculated the value of sigma yx and sigma xy. Let me write here those values, and as we know, the magnitude of the Berger vector of like this is the Berger vector. We let me highlight this one. This is the Berger vector of of second dislocation, and the Berger vector which will come in this equation, it will be from first dislocation, like the dislocation 1, and this is dislocation 2. So we are interested the effect of 1 over 2. So we are writing here is for 2, and when we write the equation of this one, we will write the Berger vector b1, and both the magnitude of Berger vector b1 and Berger vector of b2 would be equal. So we can write here sigma xx like g b square x x square minus y square divided by 2 pi 1 minus nu, this is for the edge dislocation, x square plus y square whole square. Now let me write like that. Suppose fx, this is for the per unit length. Okay, so this will be 0. When this will be 0? When x equal to y. Let me put here x equal to y, then this condition will be 0. So this glide force will be 0. Okay, so there is no force interaction, there is no force by dislocation 1 over 2. Okay, again fx by L, force along x direction per unit length of the dislocation is 0 when x equal to 0. Now you can see here, let me again reiterate, this x is equal to 0, this whole term will be 0. Okay, so this is the two case. Again, uh, fx by L greater than 0 when x is greater than y. You can see from this equation here, this x is greater than y, then what, this whole term is positive, so it will be positive. When x is less than y, when x is less than y, this fx by L will be less than 0. Okay, so it will be less than 0, like y is greater than x, so this will be complete term is negative, so this glide force will be negative. So if I want to draw this equation in the graphical form, let me write this equation: fx by L gb square 2 pi 1 minus 1 minus nu x square plus y square whole square x square minus y square. Okay, so if I write, draw this equation, like I am taking let me have different color. Okay, it's fine, let me draw with this color only. Axis by this is uh, fx by per unit length. This is various uh, x positions in terms of y. Okay, so let me write, this is plus y, this is plus 2y, this is plus 3y, this is minus y, this is minus 2y, this is minus 3y. Okay, so for the uh, dislocations with the same sign, if I am drawing, then it would be like this. In the negative direction, Okay, if I want to write this equation for opposite type of direction, then I can write with some different color, just opposite, because our line vector becomes negative in that case only. Okay. Oh, this is very hazy. Let me draw again. Okay, so this is the curve what we got. So this is fx per unit length. This is distance between dislocation. This is distance between the dislocation. So suppose we have positive dislocation, like same dislocation with the same sign. So the dislocation with the same sign arrange with each other like that fashion. So this is the most stable condition, because at x equal to 0, okay, means x equal to 0 y, that means the dislocation are arranged like this. So this is the stable condition. When x equal to y, that means again the force is 0. At x equal to, at x equal to this, x equal to 0 y, that means x equal to 0, that means the force is equal to 0. Okay, and at x equal to y again the force is equal to 0. So for the dislocation with the opposite sign, suppose dislocation with the opposite sign, so the stable configuration for that, when x is equal to plus y or negative y, means x equal to y, that means two dislocation separated by 45-degree angle, like this is x, this is y. So the dislocations are arranged in this fashion. Okay, so this is the stable configuration for dislocation with opposite sign, or this is the stable configuration for same sign. Okay, the idea is only the force between the dislocations should be a minimum or 0. That is the only criteria. And when the dislocations are arranged like this is called low angle grain boundary. Low angle grain boundary. And when dislocation arranged like this is called dislocation dipole. So in this lecture, we have understand how the one dislocation react with the other dislocation, what is the force interaction between the dislocations, and what is the stable configuration when the dislocations are of the same sign, when the dislocations are of the opposite sign. So mainly the dislocation with the same sign will form this type of configuration. When the dislocations are of opposite sign, then it will form this type of configuration. So in this lecture, uh, what we were intended, like, to understand the interaction between the dislocations, which is very much important in terms of the strengthening, because the dislocation interaction is responsible for the strengthening of a material. What we can observe in the rolled material, when large amount of dislocations are there, so there is a huge dislocation interaction, and the strength of the material is very the strength of the material increase with a very large number. So that's it for today, and we will meet in the next lecture. We will talk about the image force. Okay, till then, bye bye. If you are liking this video, please do not forget to like and subscribe this channel, and please give your valuable suggestions so that we can improve the qualities of this lecture series. Okay, bye bye. Thank you.